Okay, good morning everyone. I'm Luca Franchescoli. This is my first year here, and I'm talking about my PhD thesis about active flow control for jet noise reduction. So, but first let me start with a question. So why can't we have an airport in the city center of Madrid? Well, if we look at this kind of picture, this is the noise print generated by an aircraft in the early 60s, at the beginning of modern aviation. And as we can see, the noise print of it is quite huge. And I have to say that during the last years, we managed to have a large improvement from this point of view. And if we compare now to the beginning of aviation, we already got 80% of noise reduction from it. But the path is still long because we have a target for 2050 to reduce a further 65% with respect to what we had at the beginning of this century. And this has to be done within 2050. Now, this leads us to the field where my PhD thesis will develop, which is aeroacoustic, which talks about the study of the generation and transmittance of sound in fluid flows. Now, talking about the objectives of my thesis specifically, we have a first one, which is the design and construction of a jet flow facility where we can perform our experiment. Now, the main requirements here are to be able to perform both optical measurements, such as particle image velocimetry, in particular 3D tomographic image velocimetry, like we can see also here. Here we have the nozzle, and here the setup for particle image velocimetry, but also to be able to apply fast response probes, such as microphones or hot wires. And here you can see their applications. Here this is a semicircular rake of microphones around the jet, and the rake of hot wires at the end, close to the near field of it. Second task of my PhD thesis would be to develop active flow control strategies for noise reduction in jet flows, noise reduction, but also enhancement of the mixing properties of it. For doing this, we will investigate different possible actuators, such as microjets, loudspeaker, and also plasma actuators, and different control strategies that probably can be based on linear and nonlinear approaches, such as black boxes and neural networks. Now, the final task of the thesis will be to extract a reduced order model of the control system, but most importantly is to get results, control strategies that we can extract and we can apply also to different flow cases, such as I'm mainly talking about different Reynolds number of the jet flow. Now, how to achieve this kind of task? The state of the art in the experimental aerodynamics are basically the snapshot PIV, which is the PIV that also my other colleagues talked to you about, which allows us to get an instantaneous flow field, the reconstruction of it, as you can see here from the right, but in which we typically lose the temporal resolution of the flow field. On the other side, we can use fast response probes, which are like these ones. These are hot wires, which gives us a continuous signal with a very high temporal resolution, but where we don't have any kind of spatial resolution. Spatial resolution is in just one point. It's a pointwise measurement. So what is the task for us? The task for us is to manage to combine the two good side of the two measurement technique. And what we want to do is to estimate the flow field in between two PIV snapshots. If the green line is the instant where you can get a PIV flow field reconstruction, what you're missing is to have the flow field in between the two PIV snapshots. So what we are planning to do is to enhance the temporal resolution of our snapshot PIV, exploiting the data from the probes. Basically, the idea is to act lately on the jet flow using the probes, which are in some sense informed by time to time of the flow field estimation done with the PIV. Now, why this is important? Why we want to have this kind of estimation? Because if we manage to do this, we can have both a spatial resolution from the flow field reconstruction, but also a temporal resolution of the flow field, which will allow us to get also the pressure distribution of the flow field, which is strongly linked to the noise sources of it. Now, the literature review of what is already done, it can be done in these fields. From the point of view of the flow field estimations, we have linear methodology, such as extended proper orthogonal decomposition that works on the correlation between the probes measurement and the PIV measurements. Then we have also works depending on the positioning of our probes and the application of nonlinear methodologies such as neural network to get this kind of flow field reconstruction. From the point of view of the jet aeroacoustic, we have important works for the acoustic analogy, which then wants to simplify our study on the jet flow, but also studies on the noise sources of jets. The last one is interesting because it is in some way it's doing something similar to what we are planning to do. The timeline for my PhD research is going to be, for the first year, focused on from the point of view of the acoustic jet facility, on the building and designing of the preliminary one, which is already built and where we could already test our measurement techniques. And we're working for the second year for an upscale facility. And lastly, for the last year, we are planning to implement actuators for it. From the point of view of the flow control and estimation, now we're working on the jet flow feature estimation using the different kind of approaches, linear and nonlinear. We will move to the control using the probes measurement, and hopefully in the end to also apply a closed loop control on it, depending on the probe measurements. First preliminary results will be shown during the 3 conferences this summer, and also our preliminary jet facility is in the process of being replicated now in India. Thank you for your attention.